Okay, so for this problem, a stationary firework explodes into 3 different fragments that move in a horizontal plane, which means that the collision is actually, not the collision, but the general idea of this is in 2D, so we have to consider usually x and y directions. The fragment of, they just give us information for the balls, which is all denoted inside the diagram. Use a principle of conservation of momentum to determine theta. If we look at it, we see that if we multiply 1.5 times 8, 2.0 times 6.0, cosine theta, turns out the x components always cancel out no matter what angle. So we actually have to consider the y component. I'll write it out to make it a little bit more clear. So in the x direction, the left side, the left ball, is like this, cosine theta, and it goes to the left. And this has to be equal to the other side, 1.5, 8.0, cosine theta, because the left and right have to be equal to each other directions. And then it turns out you get infinite solutions because 2 times 6 is 12 is equal to 12 cosine theta. So we actually can't deduce anything from the from the x direction, so we have to use the y direction. So then let's actually use the top ball as the left side and then the bottom 2 balls for the right side. So we have 3.0 meters times 7.0 meters per second is equal to sine theta times 12, or I shouldn't do too much, 6.0 plus sine theta of 1.5 of 8.0, and then you get 21 over 24 is equal to sine theta. So sine inverse. I'm kind of skipping around with the calculations, mainly because you should be able to solve for linear equations. The only thing that's really important is the idea or the concepts behind the problem. So then you get 61 degrees. And notice that this is in degrees, and if your calculator is in radians, you would get something around like 1 radian. But yeah. Calculate the ratio of kinetic energy of fragment of mass 2.0 and the kinetic energy of fragment of mass 1.0, 1.5 meters. So let's calculate the top and then the bottom, and then we'll take the ratio. So the top is, I should mention that kinetic energy is equal to 1/2 mv squared. So the top will be 1/2 mass 2.0 m times the velocity. Here it says 6, so 6.0 squared, which is around, these cancel, 36 m joules, because of kinetic energy. And then for the bottom, it's going to be 1/2 times 1.5 m, which is going to be 8.0 squared, 32, 48 m joules. So that turns out that it's 36 over 48, which is 3 over 4. So the ratio is 0.75. The space probe Rosetta was designed to investigate a comet. The probe consisted of an orbiter and a lander. The orbiter had a mass of 170 kg and the lander had a mass of 100 kg. When the two parts separated, the lander was pushed towards the surface of the comet so that its change in velocity towards the comet was 3.0 meters per second. Assume that orbiter and lander were in an isolated system. The orbiter moved away from the comet during separation. What was the change in speed of the orbiter? Okay. So it's saying that the orbiter actually moved away from the comet. This is towards the comet. What is the change in speed? So initially our momentum was 270 times 0, because we're not technically moving. I should say that it's 100 plus 170 because they were together. Multiply 0 meters per second is equal to 100 kg times 3.0 meters squared per meter. Minus 170 kg v x meters per second. So then this simplifies into 170 kg vx is equal to 300 so then it becomes around 1.8. Okay, last problem. A ball X moves towards a horizontal frictionless surface and collides with another ball Y as illustrated. So the balls stick together after a collision and then travel along AB. Calculate to 3 significant figures the component of the initial momentum of ball Y that is perpendicular to AB. Okay, so initial of Y that is perpendicular to AB, so we're asking for the vertical component. That's what the component of that is perpendicular to the line AB means. So we actually need to use angle. So our component of the initial momentum, so since it's momentum, we actually have to multiply by kg, our mass. So 0.20 kg times 6.0 meters per second times sine 60, because it's y component, so it's going to be 60. And then you have to calculate this out. And then it's around 1.04. By considering the component of initial momentum of each ball perpendicular to the line AB, calculate to 3 significant figures v of x. Okay. So since we know that we're going up 1.4, this is ball y. So I have to calculate ball x. It's going to be mass times velocity, so 0.300 kg. Our velocity is going to be Vx sine of 60. I hope that makes sense. And then you can just divide it. 1.04 divided by 0.300 kg divided by sine 60 which is equal to Vx ms negative 1. And then it turns out that V is actually 0. I meant 4. 4.00, sorry. Show that the speed of the two balls after the collision is 2.4 meters per second. Okay. I think there's two ways to approach this using kinetic energy and momentum. Since it's frictionless, that means that it's elastic, I think. Either way, we can compute this using momentum, but using it in the x direction. So initially, our x direction is going to be mass 0.300 kg times cosine 60, and then the same thing for the other one. And then that's equal to x plus y, the mass of it, multiplied by v of x, what we're solving for, or vf, because v of x was the velocity of x initially. Yeah, and then you have to calculate it. So then, calculator moment. If you have a good calculator, you can actually just type this all on one line. Unfortunately, I do not have it on hand, so. And then we get that the left side will be 1.2 kg meters per second is equal to 0.5, or 1/2 basically, kg v of f ms negative 1. So then we get 2.4 kg is equal to v of f ms negative 1, which was to be shown.